a low activation energy. Is this reaction endothermic or exothermic, or is it a bad?
It's bad.
How do you know it's a bad reaction?
It looks bad.
Got a rash? Anyone have a bad reaction on the spring break? Got a rash? Poison oak, poison ivy? Bug bites, ant bites, tick bites, flea bites. I got 2 dogs. This is going to be a bad tick season. I'm always picking ticks off my dogs now. And then, of course, I find some of myself crawling up my leg on my socks. It's not a...
Does breaking your hand count as a bad reaction?
Yeah, so this reaction, endothermic, exothermic, or a bad reaction? How do you know it's exothermic? Because
energy of the products.
Yeah, energy of the products is lower than the energy of the reaction. Yes, so this is an exothermic reaction. Now, again, just to review, which part of the reaction energy diagram gives you information about thermodynamics? Yeah, so delta H. So note that for thermodynamics, all we're looking at is the energy of the reactants compared to the energy of the products. What part of the reaction energy diagram gives you energy? Gives you information about the kinetics, how fast or slow the reaction occurs. Yeah, EA. So note that reaction rate tells you what happens in between going from the reactant to the product. So again, thermodynamics only deals with reactants and products, the initial state and final state. Reaction rates or kinetics tells you about what happens in between. Okay, so let's talk about this one. So in Chem 1A we talked about thermochemistry. So as a review, is heat the same as temperature? Okay, so why don't we do this? I put some answers down here. So is heat the same as temperature? What are the 3 factors that determine the amount of heat transferred? A rock and gold cup lie in the middle of a parking lot on a hot day. Which object contains more heat? And then finally, part D, how is delta 8 calculated? So some of the answers are down here on the bottom of the slide. So I'll let you work on that for a minute or 2. You can discuss this with the person next to you if you want to. I hope after spring break we were away for 10 days, so you remember, 11 days, you remember the names of your lab partners, the names of your colleagues in class. Okay, so is heat the same as temperature? I didn't put in, like, give reasons or why, so should we just move on? You don't need an explanation? You know, you have the right answer, so you need an explanation.
We don't know why. I just know.
You just knew the right answer, but don't have a reason for it. So you're just guessing? But if you guessed right, that means you probably have some idea. Okay, so what's the definition of temperature? Yeah, so temperature is defined as now temperature, we can say that this tells us how fast or slow a substance is moving, or atoms or molecules in a substance are moving. So we can say this is the average kinetic energy of a substance. So again, that tells us how fast or slow the atoms or molecules in a substance are moving. So on a hot day, the air molecules are moving faster than on a cold day. So, what's heat?
The energy transfer.
Yes, this is the energy transferred. Okay, what else?
From the system to the
Okay, so let's say the energy transfer between
substance.
two objects due to a difference in temperature. So, you know, when you meet a person, maybe you'll shake that person's hand, and then you can figure whether heat is transferred. So, if your hand is the same temperature as the hand of the person you shook, is heat being transferred?
No.
If your hand is hotter than the other person's hand, is heat being transferred?
Yeah, it is.
Okay, part B, what are the three factors in terms of the amount of heat transfer? Yes, the temperature is one, because that's in our definition of heat. What other factors are involved? Yeah, mass. And yeah, so like Danielle says, three factors are mass, temperature, and specific heat. Now note that those three factors are in this heat equation here. So I put this heat equation Q, which is the symbol for heat, equals M times S times delta T, where M is mass, S is specific heat, and delta T is a change in temperature. Okay, let's go to part C. A rock and gold cup lie in the middle of a parking lot on a hot day. Which object contains more heat? Neither? Why neither? Because yeah, heat's the transfer of energy. So it's actually another type of energy contained in those substances, and then that energy is converted into heat. And you remember that energy inside atoms and molecules, which is converted into heat. What is that called? That's called. It's more specific than that. It's called. It's actually one of the two driving forces. Go back here. It's either enthalpy or entropy. So the energy inside those atoms and molecules, which is converted into heat, is called enthalpy. Okay, let's go to the next one. The first law of thermodynamics tells us energy can be converted from one form or one type into another type. So which equation of all these things in here represents the first law of thermodynamics? There's only, we have one, we only have three equations here. You have three choices based on the equation on this slide here. Yeah, so for the first law, this one? Yeah, have you guys seen this equation before? Delta H equals, this symbol here, sigma, is the sum of the delta H of formation of the products minus the sum of delta H of formation of the reactants. Yeah, this is called Hess law. This is used to calculate delta H for reaction. Actually, this is part D. How does delta H calculate? That's part D. So the first law of thermodynamics is either going to be this equation or that equation. Yeah, so the first law is represented by this equation here. So this equation tells that delta E, where E is the internal energy. Internal energy is the energy inside atoms and molecules. That can be converted into either heat, which is Q, or work, which is W, or both. Okay, so this is what the first law tells us, that the energy inside atoms and molecules can be converted into either heat or work. Okay, so now we're looking at three different types of energy here. We're looking at the conversion of one type of energy to another type of energy. Okay, so let's just take a look at a few examples. A hydroelectric dam. We're on the west coast. This is where a lot of our electricity is made. A battery and then a car engine. So what I'd like you to do is to describe the conversion of one type of energy into another in each of these three situations here. Has anyone ever been to the Hoover Dam?
Yeah.
Oh, good. So then you know how a dam works. Okay, maybe we can draw a picture of how a dam works. So let's see the dam. Here's your structure of your dam. Yeah. What else is there? What's on one side? Water. Okay, we need water. So you need a body of water here. Usually this can be a lake or a reservoir. Okay, and this water is fed by rivers. And what does the water do? It is to generate electricity. It falls, so it's going to fall. Here's our water, and then what does it do? Yeah, it spins the turbine. Here's the turbine. So it's going to spin that turbine. And then in physics, is it physics 2B or 4B or 4C where you learn about electricity and magnetism? 4B? 4B and 2B? So let's see, when you have a magnet and you have a coil and it's spinning, that generates electricity. So you got your turbine, you got those magnets and coils in there, and that generates your electricity. Okay, so can you, based on that picture there, can you describe the conversion of energy from one type to another?
You want like the first and last, or you want all the ones in between?
Yeah, all ones in between.
Oh.
Yeah, so you figure out the first, the start and the finish, but what happens in between?